In an age where climate change is no longer a distant threat but a present crisis, the search for clean, reliable energy has never been more urgent. Among the options on the table, nuclear power has always held a unique promise: vast amounts of energy with zero carbon emissions. But that promise comes with a shadow. Meltdowns like Chernobyl and Fukushima have etched themselves into the public memory, fueling fear and resistance. Waste that lingers for thousands of years, high costs, and the threat of weapons proliferation, all of it paints nuclear power with a brush of danger. At the heart of this dilemma lies uranium, the fuel used in almost every commercial nuclear reactor today. While effective, uranium reactors are complex, expensive, and generate waste that remains hazardous for millennia. Even worse, some of the byproducts can be repurposed into nuclear weapons, making them a geopolitical risk. It's no surprise that, despite its clean credentials, nuclear power remains one of the most controversial forms of energy in the world. But what if there was a different path, a safer, cleaner, and more abundant alternative? Enter thorium, a silvery metal that most people have never heard of, but which could hold the key to revolutionizing nuclear energy. Thorium isn't just common, it's about 3 to 4 times more abundant in the Earth's crust than uranium. It's also not fissile on its own, meaning it doesn't start a nuclear chain reaction unless it's stimulated by another source. This makes it inherently more stable, and much less likely to spiral out of control. In theory, thorium reactors are incapable of meltdown, and their waste products decay faster and pose far less long-term risk. They also produce virtually no plutonium, the key ingredient in most nuclear weapons. So why haven't we been using thorium all along? To understand that, we need to look at the science. Traditional nuclear reactors split uranium-235 atoms to release energy, a process known as nuclear fission. Thorium, on the other hand, must first be converted into uranium-233 inside a reactor before it becomes usable as fuel. While this extra step adds complexity, the benefits are profound. Thorium fission produces less neutron radiation, which reduces the wear and tear on reactor components. It also generates significantly less long-lived radioactive waste, cutting the storage challenge from thousands of years to a few hundred. This makes it far easier to manage, and much less of a threat to future generations. And because the thorium fuel cycle is more resistant to runaway reactions, the chances of catastrophic failure are dramatically lower. Innovators around the world have taken notice. Several new reactor designs are being explored to unlock thorium's potential. The most promising among them is the molten salt reactor, a design where thorium is dissolved in liquid salt and circulated through the reactor core. This design operates at lower pressures and higher efficiencies than traditional reactors, making it both safer and more economical. If the reactor begins to overheat, the salt expands and slows the reaction, a built-in safety feature that mimics nature's own feedback systems. Other designs, like pebble bed reactors, offer similar advantages, using compact fuel units and passive safety features to minimize the risk of overheating. Countries like China, India, and Norway are investing heavily in thorium research, recognizing its potential to reduce energy dependency while addressing environmental and safety concerns. If you've made it this far and you're fascinated by the future of clean energy and breakthrough science, take a moment to hit that like button and subscribe. We dive deep into game-changing innovations like this every week, and your support helps bring these stories to more curious minds around the world. Now, let's look at the path ahead. But let's not romanticize the road ahead. Building a thorium-based future won't be easy. There are still major hurdles to overcome, technical challenges, regulatory barriers, and a lack of commercial-scale experience. Because thorium was never widely adopted during the nuclear arms race, it never received the funding or attention that uranium did. That means the infrastructure, supply chains, and engineering expertise we've built around uranium simply doesn't exist yet for thorium. Then there's the issue of public perception. Despite its safer profile, thorium reactors are still nuclear, and that word alone is enough to spark fear. Convincing the world to embrace a new type of reactor, especially one still in development, will require transparency, education, and proven results. Still, the opportunity is too big to ignore. As the planet warms and the clock ticks, thorium reactors represent a chance to reimagine nuclear power, not as a dangerous compromise, but as a cornerstone of a sustainable future. With continued investment, rigorous testing, and global cooperation, we may one day see thorium take its place alongside wind, solar, and fusion as one of the clean energy pillars of the 21st century. Because in the end, it's not just about technology, it's about choices. About whether we're willing to evolve, to question the status quo, and to invest in safer solutions. Thorium may not be a silver bullet, but it just might be the smartest nuclear option we've never used.